Hello everyone and welcome to this video. The goal of this video is to give you a basic introduction of molecular dynamics simulation. So keep in mind that this is a very basic introduction. I will skip a lot of details to keep it simple, and we will talk more about this in the future. But hopefully this video should give you a basic understanding of what are the main ingredients that are at the roots of the molecular dynamics method. So what is the goal of the molecular dynamics method? Well, the premise is as follows. So you start with a given number of atoms, a given number n of atoms. So you have a collection of atoms, and you want to be able to simulate, to predict how those atoms will be moving according to time. How will be the displacement of all the atoms at different time. Okay, so you want to be able to predict what will be the trajectory of all those atoms, what will be their motion according to time. Okay, so the way to do that is you will be to apply the molecular dynamics method. What you need is to start first where your atoms are initially. What is their initial position? For this, we typically rely on their initial vectors. So for example, this is atom 1, atom 2, atom 3. What you know is their initial position. So this will be a vector R1, vector R2, R3, etc., which gives you the initial position of the atoms. What you also need to know is the initial velocity of the atoms. Okay, so this depends potentially on the temperature. If the temperature is very high, then the atoms will be moving very fast. Or maybe you want to start with an initial configuration where the atoms are initially immobile, so they have a velocity of 0, and you want to know how they will be moving and start moving in the future. So in any case, you need to know the initial position and the initial velocity of those atoms. The second key ingredient that you need are the interatomic energy. So what is the interatomic energy? This is the energy in between each atom. Each pair of atoms potentially will have a given energy. Okay, so if you have a collection of those atoms, 1, 2, 3, 4, 5, etc., with a collection of those n atoms, every atom will apply small forces on the other atoms. For example, here you have the force applied by atom 1 on atom 2, but you also have a force applied by atom 2 on atom 1, and those two forces are the same magnitude, but opposite direction due to the principle of action-reaction. But atom 3 will also apply a force on atom 1, etc., and all the other atoms potentially can apply a force on each other. So this is a very important ingredient that you need for the molecular dynamics. If you want to describe the motion of the atoms, you need to know what are their forces. And to know their forces, you need to know what is the energy between each pair of atoms. For example, if you have those two atoms, 1 and 2, you need to know what is going to be the energy U12 of interaction between atom 1 and atom 2, which will depend on the distance. So this will be the distance between atom 1 and atom 2. So what are those interatomic energy and how can we describe them? So there might be different contribution. If you have two atoms, 1 and 2, there might be different contribution to their energy of interaction. Okay, so the energy of interaction between those two atoms. First, you have the Coulombic interaction. So if those atoms have a charge, if you have some cations, etc., then you will have a Coulombic interaction, which is 1 over 4 pi epsilon 0 times the charge of atom 1 and atom 2, the product of the charge, divided by the distance. So the Coulombic interaction is proportional to the inverse of the distance in between the two atoms. Okay, so this is the first thing, Coulombic interaction. This is when you have some charges. The second thing is the Vander Waals interaction. Van der Waals interaction comes from dipoles. Each atom has some dipoles. It can be either permanent dipoles or an instantaneous dipole. And those atoms, those dipoles, mutually interact with each other. They have a given interaction of energy. Those are the Van der Waals energy. The Van der Waals energy are typically always cohesive. They cannot be repulsive, so they are negative. Okay, energy is negative when it's an attraction, and it's always proportional to 1 over R6. Okay, so this is the Van der Waals interaction between two atoms. It comes from the dipole-dipole interaction. And the last type of interaction that you can have is the electronic repulsion. If you have two atoms that comes very close to each other, then we know that the electrons around each atom will not want to overlap. You cannot have two electrons at the same position at the same time due to the Pauli exclusion principle. So it will cost you a lot of energy to have two atoms come very close to each other. Okay, so we don't have a very clear representation of what would be the right mathematical formula to describe the energy that it costs to have two atoms comes very close to each other and to have the atoms starting to partially overlap with each other. But so this is a very a problem that should be described by quantum chemistry, a quantum representation of the atom. But typically, we will just describe it by a function that increases very fast as you go towards zero. So a function that goes to infinity because it costs you an infinite amount of energy if you want to have two atoms that would overlap with each other. So coming together, so if you represent all those three contributions to the energy, it typically looks like this. Okay, so if I plot now the energy according to the distance, so you have first the electronic repulsion. So the electronic repulsion will only be at small distance. So at distance very close to zero, it will cost you a lot of energy if you want to have the two atoms overlap with each other. Okay, so this is the repulsive energy. It comes from the electronic interaction. Okay. The second thing is the attractive energy. So it can be Van der Waals, for example. The Coulombic interaction can be either repulsive if you have two atoms that have the same charge, or attractive if you have an atom that is positive charge and negative charge. But the Van der Waals interaction are always attractive. So the Van der Waals interaction will typically look like this. So they also decrease with the distance, just like the electronic repulsion, but they decrease much slower. Okay, so this is an interaction that the atoms will undergo even at higher distance. So the Van der Waals interaction typically look like this. Okay, so for example, a model for the electronic interaction, for example, is given by the Lennard-Jones model, which model the electronic repulsion between the atoms as a term that is proportional to 1 over R12. So this is also a function that decreases up to 0 at infinite distance, that becomes infinity at very small distance, but it decreases much faster as 1 over R12, much faster than the Van der Waals terms that decreases as 1 over R6. And the one that decreases the slowest is the Coulombic interaction that only decreases as 1 over the distance in between the atoms. So altogether, if you have those two contributions, so the repulsive term will dominate at very small distance, okay, because it increases much faster as 1 over R12 than 1 over R6 or 1 over R. But at large distance, this will be the Van der Waals interaction or the Coulombic interaction that dominates because it decreases much slower than the 1 over R12. And in between, you will have a balance between those two terms that should give you a function that looks like this. So this is a general shape that we expect for the energy between two atoms. We expect the following feature. We expect that it's going to be repulsive at very short distance, so the energy should always go to infinity at a very short distance. This is when the distance goes to 0. This comes from the electronic repulsion. Two atoms cannot overlap with each other. at very large distance, when the distance go to infinity, then the energy should also go to zero. This is because if the atoms are very far away, then they don't see each other, so they should not have any interaction with respect to each other. So the energy of interaction should be zero. And in between, you should have an equilibrium position. So you should have a minimum of energy here at a given distance r0. This is going to be the equilibrium position between the atoms. This is the distance that they would have at zero temperature. If they go at a minimum of energy, this is the distance that they would have. They would be at a distance r0 from each other. So the next step is, if you know the energy, how do you get the force acting between the atoms? Okay, so if you start from the energy, again, the energy will always look like something like this. This is the energy as a function of the distance, goes to infinity at very small distance, goes to zero at very large distance, and have an equilibrium position somewhere in between. Okay, so now the question is, if you know this energy, what will be the force? Okay, so this is a general problem. If you know the energy for a given type of interaction, how do you get the corresponding force? Well, the answer is as follows. If you have, for example, an atom here, the atoms will want to go towards the minimum of energy. So necessarily you will have a force that pushes the atoms to go towards the position r0. On the other hand, if you have an atom here, then again the atoms will want to go towards the equilibrium position. It wants to minimize the energy, so it will want to go this time towards the left. So what you see here is that the atoms always want to go towards the equilibrium position, and the magnitude of the force that pushes them back towards the equilibrium position, is given by the slope. If you have an atom that is here, very close to the equilibrium position, then the slope is relatively modest, relatively low, so the force will be quite small. You have a low propensity that will push the atoms to go back towards r0. But you have an atom here with a very high slope, then the force will be much higher. You will have a much more intense force that will push the atoms to go back towards a more stable position with a lower energy. So what matters is the slope of the energy. Okay, so this can be calculated by calculating the gradient. And in fact, so this is the case with many interaction. The force corresponding to the interatomic interaction is given by minus the gradient of the energy. So if the energy has a negative slope here, then you will have a positive force that will push the atoms towards the right. If the slope is positive, then the force will be negative. So that's why you need the negative sign here. So if the interaction only depends on the position, just like here, then the gradient is just minus the derivative of the energy with respect to r times a unit vector, which would be just the vector that goes from atom 1 to atom 2, and that has a norm equal to 1. Okay, so if you have the following energy, the energy with respect to the distance, then it means that you can get the force just by differentiating the energy. You can just take the derivative of the energy for every position to get the force. So if you are at a distance lower than r0, then the energy has a negative force, so it means that the force will be positive. Okay, it will tend to push the atoms to go towards the right. Then if you have a distance that is larger than r0, then it means that the slope of the energy is positive. Then it means that the force will be negative. It will tend to push the atoms to go towards the left. And here at this point here, you have an inflection point. It means that after that, the slope here is 0, then the slope keeps increasing, you reach the inflection point, and after that the slope keeps decreasing and go back towards 0. So since the force is equal to the slope of the distance, it means that here the force will be minimum. This is where you have the maximum slope for the energy, and then the force will go towards zero at infinite distance. At infinite distance, again, the atoms are infinitely far away from each other, so they should not see each other. They should not have any interaction forces in between them. So now the next step is, if you know the energy in between each pair of atoms as a function of their distance, how can you get the motion of the atoms? How can you determine the trajectory of these atoms? So this is basically the goal of the molecular dynamics method. It relies on a cycle, which relies on different steps. It's an iterative cycle, and we will see the different step here. So as I mentioned before, the first step is that you always need to know what is the initial position of the atoms at an initial time 0. Okay, so you need to know for each atom going from 1 to n, for all the n atoms, you need to know what is their initial position, and you need to know what is their initial velocity. Okay, initial velocity at time 0 for all the atoms. This is the first thing. You need to know what is the initial configuration. Okay, the collection of all the position of the atoms at a given time is called a configuration. Based on that, if you know the position of atom 1, position of atom 2, and for all the other atoms, then you can get their distance. You can get the distance between atom 1 and atom 2. And if you know the distance, then you are able to calculate the energy. You have a given model, can be Lennard-Jones, can be something else. We will see different models for the future. But you have a model that will give you, for each atom I and j, as a function of their distance, what is their energy of interaction? What is the energy Uij of interaction between atom I and atom j? And if you know the energy between all pairs of atoms, the energy of interaction, then you can calculate the total energy of your system, which will be the sum of all the energy of all pairs of atoms. So for example, you will sum for all the atom I larger than j. Okay, so for all the pairs where I is larger than j, larger so that you avoid counting each pair 2 times. For example, you should not count 2 times the interaction energy between atom 1 and 2, and then the interaction energy between atom 2 and 1. So you can get the total energy by summing the energy of each pair of atom. This is the step number 2. This relies on a model that gives you the energy of each pair of atoms as a function of their distance. Okay, so the next step is, if you know the energy, just like we just saw, now you can calculate the force. You can calculate the force. The force applied by a given atom j on atom I will be equal to minus the gradient of the energy. Okay, so if you know the energy as a function of the distance, you can differentiate it. You can take the gradient in order to calculate the force. And if you calculate the force applied by atom j on atom I, you can calculate what is the resultant force applied on atom I. What are the sum of all the forces that are applied on atom I? This will be just the sum of all the atom j, all the other atoms j that are different than I. Each atom j will apply a force on atom I. If you take the sum of all those small forces applied by all the other atom j inside the system, then this will give you the total force applied on atom I, the resultant force. Okay, so this is step number 3. You differentiate the energy to get the force. You get the force applied on each atom I. The next step is, if you know the force, then you can apply Newton's law of motion. Why? Because if you know the force and if you know the mass of each atom, then you can say that the acceleration of each atom is given by the force divided by its mass. Okay, so this is the Newton's law of motion. The force is equal to mass times acceleration. So if you know the force, you can calculate the acceleration. Okay, and the last thing is that if you know the initial position of the atom, you know its initial velocity, and now you know its acceleration, then you can predict how the atoms will be moving after a small increment of time. So now what you can predict is, you know the acceleration, so you know how the velocity of the atom is changing, so you can calculate the new velocity of each atom after a small increment of time dt. And if you know that, you know how the velocity is changing, so you can calculate what will be the new position of the atom, of each atom, after a small increment of time dt. So this relies on a numerical integration. If you know the acceleration, you can integrate it in order to get the position and how the position is changing according to time. If you know that, then you can calculate, you know the new position, the new velocities at a small time dt, so you can calculate the new energy at small time dt. You can calculate now the new forces at a small time dt, so you can calculate the new acceleration of each atom after a small time dt. Again, you can do a numerical integration to get now the new velocity at a time 2 dt, dt plus dt. So doing so, you will be able to calculate what will be the new velocity of the atoms according to time. Doing cycles and cycle in an iterative fashion, you can calculate how the velocity is changing according to time and how the position is changing according to time. So this rely on several things. First, you need to know the initial position of the atoms. So you need to know, to be able to start this iterative cycle, you need to know what is the initial position of the atoms. Okay, so this is one of the first thing that you need to know. You need to know the initial velocity. If you don't know the initial position of the atoms, you will necessarily have to guess, because you need to start by somewhere with this process. The second key thing that you need to know is what is the interaction between each type of atom. Okay, what is the form, what is the general formula that gives you the energy between each pair of atoms as a function of their distance? So there are different models for this, but basically this is probably the most important ingredient of the molecular dynamics simulation. If your model for the energy is wrong, then the whole molecular dynamics simulation will be wrong, because everything depends on that. The force depends on the energy, acceleration depends on the force, and the way the position is changing depends on the acceleration, which depends ultimately on the energy. So if the energy is wrong, then everything is going to be wrong. So this is probably the most important steps inside the molecular dynamics. This is to get a correct description of what is the energy between each pair of atoms. Then these steps here, there is no approximation involved. The force is minus the gradient of the energy. This is always right, so there is no approximation with that. This is always valid. Newton's law of motion is again always valid, as long as you are simulating a classical system that can be described by classical dynamics, classical mechanics. Then the Newton's law of motion has to be true. So again, there is no approximation here. The last approximation that you need to be careful with is to do this numerical integration. So you need to choose an increment of step dt that is small enough, otherwise your numerical integration will not be correct. Okay, so we will see, we'll talk about that in a few seconds, but basically like the things to keep in mind, the three ingredients that dictates the quality of a molecular dynamics simulation is having the right initial configuration, right description of the energy in between the atoms, and to choose an increment of time dt that is small enough. So what is the basic idea behind this numerical integration step? So there are various methods to integrate in a numerical fashion the acceleration in order to get the new position, but the idea is always to do a Taylor expansion of the function. Okay, so the idea is that what you know is the initial velocity. You know the initial position, initial velocity at time equals 0. You know its acceleration, so you calculate the acceleration. And based on that, what you want to know is what will be the new position and new velocity after a small time dt. How can you achieve that? Well, what you can do is to do a Taylor expansion of the velocity. So what you can say is that the velocity at a given time t plus dt of a given atom is equal to first the velocity at t plus a small increment which is equal to the derivative of the velocity with respect to time times the increment of time dt. Okay, so this is the first order of the Taylor expansion of the velocity. There will be some higher order terms, the second order, third order, etc. But if you choose dt small enough, then it's okay to just take the first order approximation. And it basically said that if you take a small dt, then the function can be assimilated to a linear function that increase or decrease linearly with time, with a slope that is equal to the derivative number of the velocity with respect to time. So here, if you express this velocity and take its first order of the Taylor expansion, then you have a term here that is the derivative of the velocity with respect to time, but this is nothing else but the acceleration. So if you know the acceleration at a given time t, and you take the Taylor expansion, then you are able to calculate what is going to be the new velocity after a small time dt. Okay, and you can do the same for the position. If you express the position at t plus dt, you take again the first order, so zero order tells you that the position is going to be equal to the initial position at t, plus a small increment, which is the derivative of the position with respect to time times the increment of time dt. But again, the derivative of the position is the velocity. So if you know the velocity at a given time, then you can predict how the position will be changing. If you know the initial position, how will you get the new position after a small increment of time dt? So you see that here, this expression will can always be as accurate as you want, but the key is to choose an increment of time dt that is small enough so that the Taylor expansion of your function will be a good representation of the value of the function after a small increment of time dt. So the value of dt depends on the type of system that you are simulating. If you have a system with the atoms moving very fast, you will need to choose a small dt. But if the atoms are moving slower, then you can use a larger value of dt. Typically, for the type of system that we typically simulate, dt of around 1 femtosecond is typically a good choice, but it needs to be determined for every case. Again, it depends on the typical dynamics of the system. If the atoms are vibrating very fast, for example, then you will need to choose a smaller dt. dt always needs to be small as compared to the typical times of the dynamics of the atoms. So what can you do with that? Well, the key point of the molecular dynamics is that it gives you, by doing this iterative cycle, by starting from the position, then going to the energy in between each pair of atoms, based on that calculating the forces, by taking the gradient, based on that calculating the acceleration, and then giving you the new position after a small time dt, etc. The key thing is that it tells you the position of the atoms according to time. So you will get the detail for all the atoms about how their position is changing according to time. So this gives you the trajectory, okay, the ensemble of all the position occupied by all the atoms according to time. So if you start by a given position at time equals 0, the acceleration will tell you how the atoms is moving after a small increment of time. So you will get the new position for this atom after a time dt. Then after that, you will redo a new molecular dynamics cycle to get the new position at time 2 dt, etc., position at time 3 dt. So you will get the ensemble of all the positions according to time. So you will basically know how the atoms are moving, how fast and where, okay? And if you know that, you know everything about the dynamics of the system. You know first the thermodynamical properties, so you will be able to calculate the temperature of the system. Depending on how fast the atoms are moving, you will be able to calculate the pressure of your system. And if you know the pressure, you will be able to calculate the stress, for example, for a given pressure, for a given deformation. So you will be able to calculate all the mechanical properties of your system, its stiffness, etc. You will be able to calculate all the dynamical properties of your system, all the vibrational properties of the system. So you will be able to characterize a lot of interesting properties of the given material that you are interested in. The only thing that these techniques in the state that I described to you cannot give you any information now are the electronic properties. Okay, the electronic properties cannot be described here because we don't describe the details of the electrons. Okay, so we know that atoms are made of electrons, electronic clouds around a given core, but here we neglect this representation. We just say that the atoms are just points that interact with each other. So we don't detail the interatomic structure. We don't detail the behavior of the atoms inside them, how the electrons are being deformed, how they are shared between different atoms. So we cannot say anything about the electronic properties of the material. For this, you will need a quantum representation of the atoms. But for all the other properties that are classical properties that do not depend on the electronic density around each atom, then the molecular dynamics method can give you some very good prediction about the properties and the behavior of the systems according to time. You can use it for different types of materials. It can be solids, can be liquids, can be gas, can be glasses, etc. But by describing the motion of the atoms, you can basically describe all the properties that you want for any given system. Okay, so I hope this video was useful, and thank you for listening.